So, what are we doing today? So yeah, we're backpedaling a little bit to Unit 9, like I was telling you guys. This is a lesson I wanted to do in Unit 9. We didn't get to it, but I've been wanting to do it on just like a day like this where we're kind of in the middle of chapters and we have a second, so I'm going to do it today. So what are we doing? You guys, what kind of a function is this? A times b to the x power. It's an exponential function. Very good. Now, when we use e, right? You guys remember the PERT formula?
No, we do not.
P-E-R-T? All right, that's for continuous growth. Okay? A lot of times when we look at word problems, they say, you know, like every year it doubled or something, right? And so you're like, what that sparks in our mind is this idea of it just sits there, and at the end of the year, all of a sudden, it's double, right? Which some things actually do work like that. But that's not how most things really work. What happens is they continuously grow, and to such an extent that by the end of the year, now it's doubled, right? So if I was setting up an exponential function for this, you know, I'd say, if it was really doubling, then my b would be 2, right? And the x would be how many years have gone by. And however many years, that's how many times we multiply by 2, and we keep doubling it over and over again. Hopefully this is kind of ringing somewhat of a bell. It's been quite a while, about 4 chapters. But the problem with the AB model here is that it's synthetic. It's not genuine. It's not real, because it's not really just doubling at the end of the year all of a sudden. What's happening is it's continuously growing. And for that, we need the continuous growth model. You guys remember continuous growth? That's the one with the E in it. So what our lesson today is, we're going to learn how to take something that looks like a sporadic growth, AB, and we're going to convert it into an AE. Now, why do we want to do that? Well, because first of all, it's a better model of reality, because in reality things continuously grow. They do not periodically grow all of a sudden, right? But another reason is because, once again, in calculus, for those of you guys that are going to continue your math education, we use E. We use E. And typically when you have a regular exponential function, the skill of turning it into E is very helpful. So that's why we're doing it. All right, so let's go ahead and jump in. I told you guys to grab a calculator when you first came in, but your cell phones will work fine if you have one. So no sweat if you don't have one of my calculators. So go ahead and write down this problem really quick, please. So I'm gonna put some instructions up here so that we actually know what we're going to be asked to do here. So I want to rewrite this in this form instead. I want to get rid of the E. Now that's exact opposite of what I just told you what we're doing today, right? We want to turn B's into E's, but I want to start with something that's a little bit more familiar. I want to show you how the E can be rewritten as a B. It's a little bit simple. And here we go. Here's all you have to do is get your calculators out, and I want you guys to do E to the 0.693 power. Do that for me, please. What is E to the 0.693 power? Now, if you don't know how to get the E button, what you do is, if you're using my blue calculators, you push second and then LN. And you should see on your screen at that point an E with a little caret symbol, right? And that's where you put your exponent 0.693, and then you just push equals, and you're good to go. What are we getting?
1.9.
And so if we rounded that, what would we call that? It's just 2. Okay? So what I've shown you is that we can rewrite this funky looking thing here into just a normal number, right? They're the same thing. Okay, it's just that they're written differently. Today's objective, though, is to work backwards. We're going to start with the 2 and turn it back into an E. Okay? And like I said, we know why we're doing that now. It's helpful in calculus, and because it actually models real-life scenarios better. So let's go ahead and continue here then. So go ahead and write down your directions here and then the first problem. So the only part I want to change is I want to change this 5. I don't want it to be a 5. I want it to be e to a power, right? So what I'm going to do is I'm going to say e raised to what power is equal to 5. So let's write that first. Go ahead and write down e to what power equals 5. How do we solve for x? And remember? Nice job. Very good. So it's hard to remember. So it's been a while. You're going to ln both sides, right? Very good. Very good. All right. You're going to ln both sides because ln cancels the e out, and here's what we're left with. 1.609. So if you guys want to see how I'm going to do that, go ahead and push just ln of 5 on your calculator. And you should get about the same thing, right? All right. So what I've just done then is I have found that 5 is the same thing as e to the power of 1.609. Okay? So that means I can rewrite this equation without changing its value. I can rewrite this as e to the 1.609. So all I've done is I've replaced 5 with e to 1.609 because e to 1.609 is 5. That's what we just did. Okay? That's it. That's all there is to it. So I've changed it from something that, increases by, a multiple of 5 every x into something that continuously grows instead of just punctuated. So now there's kind of a shortcut here that I'm going to share with you guys at this point, okay? I would write this too, even though it's the same problem, because I like you to understand the math, but once you've got the idea of how that works, I'll share with you a shortcut just to get it done and over with. So check this out. It's pretty easy. Write down the shortcut here. All you do is you're going to put e ln 5. It's the same thing that you have here, it's just that you replace the 5 with e ln of that number, right? And that's good enough. You could actually do the calculator work and change it to 1.609 if you want to, but that's it. So now that we know the shortcut, let's apply it to this one. This would be y equals 6, and I'm going to replace that half with e to the what power? ln 1/2. Fix my ln there, it doesn't look right. ln of 1/2, that's it. So we just rewrote it. Why is it like that? Well, now we saw the steps, right? It's because you ln both sides to solve for the x. So that's kind of our shortcut there, just transforming it. Now me, I've been teaching math for a while, and I still did not remember that shortcut this morning. So shortcuts are nice just to get things done and over with, but I don't know about you, but I never remember them. What I did to get my answer is what I showed you to begin with. E to the x equals the number. So you want to know how to figure things out in case your memory is like mine. But there you go. All right, so that being said, let's actually put this to work a little bit. You guys go ahead and rewrite these real quick. It shouldn't take you too long. So there's our answers. We have this one and this. And if you want to actually turn them into a decimal like this, that's fine. All right. So, you guys remember that? A little bit? What does this represent? Good. That's our starting amount. What does this represent?
Rate.
Good, that's our rate. And how can you identify a rate in a word problem usually? You guys have great memories. It's a percentage. All right, it's a percentage. Everything's rerouted, huh? This is for growth, and this is for decay. So in other words, if you're adding that percent over time, then that would be, you'd be adding, you'd be plus. If it's a decay problem where like something's reducing, becoming smaller, then you'd be subtracting that percent. All right, and then T pretty much almost always represents time in some shape or form. So I'll leave that up there. We're going to look at some word problems, and you're going to need to have that. Huh? No, it isn't. It's on the wall. Exactly. But it's right twice a day.
How incorrect is it?
I don't know how I can answer that. Mathematically, I'm wondering how to quantify that. I guess we could look at how much slower it's going than a real clock.
So what's the decay rate?
We could just say how far it is off right now.
18 minutes off? Like behind? Or like?
I don't think it's just 18 minutes. That says 7:30.
Oh, that's not 18 minutes. When is it about?
Hey, this is fun. All right, so let's do a problem. In the interest of time, I'm going to say let's not copy this. And with the student practice, you can copy it if we have time. So I just said don't write this one. But for the student practice, I would say if you have time, I would highly encourage you. Otherwise, your notes would not be valuable to you for that problem. So yes, I would encourage you to if you can, but let's first solve it just to make sure you guys know how to do it. And if we have time to write, we will. All right, so the population of insects during the spring season increases by 5% per day. It's probably not true. I made that up, just so you guys know. Don't go quoting that in a scientific journal. Write an exponential function that represents the number of insects for any given value of time t. Let n represent the initial number of insects at t equals 0. So they're telling it, so we don't know what the starting amount is, but we're just going to say it's n. Okay. All right. So first of all, looking at this word problem, how do you know that this is an exponential problem?
5%.
It's increasing by 5%. So when something increases by a percent, that's exponential. Okay, so we know we're using that model that I've gotten written at the top up there. So now what did we say our starting amount was going to be? N. And what's our percentage here? Now we have to change it to a decimal. 0.05, right? 0.05. Now am I adding or subtracting? You're adding because the insects are increasing. And then that's it. We're going to put t here. And so here is my model. Here's the answer to A. I'll just write it down here now. Y is equal to n 1.05 t. Okay? Now, let me ask you guys this. Is it true then that the insects are just chilling and then all of a sudden at the end of the day they just pop up to 5% suddenly?
Exactly.
No. Obviously there's, I mean, it's a little bit more realistic to say, well, different ones are constant. So if you look at the population, they're constantly reproducing, right? So you could say it's constantly growing, really. It just so happens that by the end of the day, you've got a 5% growth. So since we're talking about truly a continuous growth, we should really be writing this in terms of E. Okay? So rewrite this expression as a continuous growth function. Bless you, by the way. We're good. Now it's continuous growth. Cool? So now that's a little bit more of an accurate picture of the growth. it's also easier for calculus. So there you guys go. All right. So I'm not, like I said, I wasn't going to have you guys write that one. I was just going to have you watch. I'm going to have you guys do the student practice. Get your answers first, and then if you have time, I would, of course, encourage you to copy it down so that when you look back at your notes in preparation for your final, should we have one, you have something to look at. So, go ahead. Alondra, what's our starting amount? 50 is correct. Jennifer, what is our rate? 0.25. Cleopatra, is it going to be 1 plus 0.25 or 1 minus 0.25? Good. All right, so here's our model then for part A. The final amount is equal to the starting amount times 1 minus 0.25, and then we're going to put a t. Now, I saw someone put a 0 here because it does say time equals 0. The reason they tell you time equals 0 is just so you know that that's the starting amount at t, like time equals 0. So we're not going to put a t there. I'm sorry, 0. We're going to put a t because the t represents any time. This is just the special time that gives us the initial amount. All right, so here's how it should have been written in simplified form, like that, right? And so finally, I'm going to be coming to Tammy. What is the continuous growth model for this story problem then? I'm hanging.
It's N.
No.
Wait. E. Oh, it's E. Ln 35.
You didn't do the problem, did you, Tammy?
Can I say it?
It's 0.75.
I didn't do it right.
Oh, okay. It's e to the ln 0.75. Okay, and that's a more realistic one. So yes, even though every hour you might have 25% less in your system, what's really going on is your body is really constantly consuming it. So this is a better model than the other. And that concludes our lesson. So if you have not yet written this down, this would be a great time. We still have 10 minutes of class left. We are done for the day. Here, here. Here, here.